Okay, so started to talk about entropy. So one thing I didn't say, we said that entropy, we should think about it as information content, or in the sense that if you're predicting something, how much information are you actually giving me? And so what is the one thing that should happen? So one thing we did see, right, is we saw that conditional entropy is always less than. Should probably use sigma algebra notation. So it doesn't matter. So one thing we did see was that if I condition on some information, I always have less entropy, right? Or I don't have more entropy because I gave you information. Know something then the entropy, the conditional entropy can't give you more information than the original thing. And another fact, so fact or position, prove this one. If X is measurable with respect to sigma algebra F, then what is the conditional entropy of X? Entropy of X. So if X is measurable with respect to this sigma algebra, means that F contains all the information you need to know X. Oh, so there's no entropy. Right? So there should be no entropy, right?
So it's equal to the entropy of X if they are independent.
Yeah, this is equal to entropy of X if they're independent, meaning that F contains no information relevant for X. This is the polar.
So entropy is we're thinking about what information we don't have.
It's how much entropy is it giving me to see this random variable? How much I measure, X is a measurement. I measure something, how much information did I get? For example, I want to measure the temperature of the molecules in this room. How much information did I get? I got some information about the kinetic energy by measuring temperature. And how much information did this really give? It didn't give me the complete information. It didn't give me the exact state of the molecules. That would be very, very high entropy, right? Giving me the exact position and momentum of each of the molecules. Let's work classically now. Don't give me the face of quantum. Don't give me the quantum face.
No, I don't do it.
I was joking. So I mean, measuring the position and momentum of every single one of the particles in the room, this would be maximal entropy, right? This would be like.
Wait, but if we know everything about X and the entropy is zero, that means that entropy in some way measures what information we're
so
missing.
Conditional entropy is measuring how much information does X. If I measure X, how much information does X give me? But I know F.
Oh, okay.
Given the information that I know, if you think about a random variable here, X conditioned on Y, if I know the measurement Y, somebody already measured Y, told me what Y is. So you measure temperature, you tell me what the temperature is. How much missing information do I have if I know all the positions of all the particles?
No,
right?
no information.
That's right. So one direction is always if you know all the position and momentums of all the particles, then you actually know the temperature. So the conditional entropy of the temperature would be zero, but the other way around, you would have, because temperature does not tell you the complete state of
Right.
Okay. Right? It's just partial. Okay, so this proposition proof. Well, it's very simple. Remember, what is conditional entropy? Conditional entropy is expectation of what? Of random entropy, right? What was random entropy? random entropy was the entropy, the conditional, the entropy of, let's write here, so it's the entropy, so it's going to be a random number because it's the entropy of a random probability measure, right? It's the entropy of the random probability measure, which is the probability measure that x is equal to something conditional on f, right? This thing is a random probability measure, right? For every single one of the instances of this probability measure, I get a probability vector. This probability vector feeds into this to give me a number. Since this number depends on a random vector, it becomes a random number. Okay, so this is a random entropy, and I take expectation of this with respect to it. Right? Now, if x is measurable, what is this guy? If x is measurable with respect to f, so if x is in f, which means x is measurable with respect to f, that's just a notation, right? Then what is the probability that x is equal to little x conditional on f? What is this?
Just
This is just the conditional expectation of the indicator, right? And the indicator is measurable with respect to this guy. So it's just the indicator itself. So this is the indicator that x is equal to x, right? So this is a number which is either 0 or 1, but it's a random number. Okay? But this probability vector, so the conditional probability vector, right, is just a vector that says for every little omega, it says 0 in all the places except for one place where it says 1. Right? So this probability vector, this is a random measure now, mu f. So we need to, so what is this thing? This is a function of omega, right? This is a function of, so let's look at the condition, right? So I'm going to write this. This whole thing is a function of omega. So when I look at it as a probability measure, okay, if I define mu little omega of x, this is going to be the probability that x is equal to x conditioned on f. This thing evaluated at omega, right? So if you want to be very, very formal, for every little omega, I get a probability vector, right? So random probability vector, and I'm measuring its entropy. Okay, then this guy, so mu omega, right? For every omega, mu omega is just some delta of some x, right? It's just delta x omega. Right? Because it's exactly, because x is measurable, it's exactly the indicator that x is equal to something. What is x equal to? On omega, x is always equal to x of omega. Okay, so it's just a vector. For if we fix an omega, this will say 0, 0, 0, 0, 0, 1. Where will it say 1? At the exact place where x, big X is. Okay? But what is entropy of a delta measure? Entropy of any delta measure, right? Delta alpha here, just to live in some space, right? The entropy of a point mass, what is that? It's just 1 log 1, right? Okay? So this was a very, very elaborate way of saying that this is just 0. Okay, I really spelled out all the little letters and dotted all the I's, right? So all of this implies that HF of X is 0 whenever X is measurable with respect to that. Okay.
There is another formula for this HF, I guess it's in the book of yours. There is also another formula that given
I
the
proved it. What?
the HF, the random variable, we can like sum over all the options and
That's what it says here. That's what it says here. You look at this. You look at this omega. This. What does this say? This goes. You sum over all possible x's. Okay. This cannot take more values than. And you have the convention that 0 log 0 is 0. Okay. Minus, and then you have the probability that x is equal to x conditional on f. So this is a random number log this probability. This is the exact formula. Okay. You have to make sure that this converges for every, but okay, it's not negative. So if you assume that 0 log 0 is 0, then this makes sense. And this is a random number. Okay? Maybe this is the formula.
yeah.
So that's what I want. But that's exactly what this says. This is this vector, right? For every omega, I get a vector. I do the entropy of that vector and average all the vectors.
Ariel,
Yes.
could I say, I mean, if I would go like h of x condition of on x is zero out of the because of the formula that we proved last time
Mm-hmm.
for two variables.
Mm-hmm.
Now, if x is measurable with respect to f, it means that the sigma algebra generated by x is contained in f. It will prove this, right? I mean, we didn't even prove anything about if you take two sigma algebras.
You're right. So exercise.
But I don't know if it's the right direction.
Exercise. If G is contained in F. Okay, so we have two sigma algebras, one contained in the other. Okay, what is the relationship between conditioning on G and conditioning on F?
That gives you more information.
F gives you more information,
The more you know, the less of
so the entropy here should be less. Okay, and entropy, remember I always say that independence is completely non-intuitive, entropy is completely intuitive. Everything your intuition tells you should be correct. That's actually the biggie, the real benefit of entropy. It's really easy to work with because it's really intuitive.
But the definition itself is
Non-intuitive.
somewhat, yes.
Well, once you define it properly, what's information? I gave you motivation why to define it this way and how to get this.
Yeah, but I mean, what we did so far gives you like intuition why, I mean, roughly if it's bigger, if it's smaller, what it means. But the
Yeah.
exact number,
No, numbers. That's something else. Well, you can't think logarithmically, right? It's a logarithmic scale, so we don't know how to think logarithmic. Yeah, okay. Of course, some things are intuitive. Otherwise, it would be something we see, right? It took a while to understand what entropy is. In fact, it's very intuitive, and we don't understand entropy at all. Physically, in terms of physics, we don't understand information. There's a big paradox there. What does information mean? This is a deep thing. I mean, it's a philosophical thing. As soon as we understand it, we will stop being philosophy and we start being mathematics. That's what
if
usually
you're
happens.
working in computer science and you use log with basis 2,
Yes.
it can be like, I know, number of bits that.
Yes.
Yeah.
So entropy of a probability distribution, right? It's a function of the probability distribution. It's not a function of the actual random variable. Is the number of bits you need up to rounding error. So entropy will give you a number. You need to maybe round up because it's the number of bits to the nearest integer. But it's the number of bits, the minimal number of bits you need to sample this distribution on average. Okay. So, for example, if you have a uniform distribution, then you know it's just log 2, right? That's if you use log 2 bits. But I mean, if you're using log e, like natural log, like I'm using, then it's not the number of bits, but the number of e possible, I don't know, bits that have e possibilities, right? Not 2. So like that. Okay, you can imagine what that means. But on average, it means that if you have 1/4, and then 1/2, right? So on average, you need what? 1.5 bits, something like that, right? You need 1 bit to say if it's 1/2 or the other half. And then half of the time you need another bit, right? So you need 1.5 bits on average. Okay, and I think if you work it out, right? I mean, if you do 1/4 times log 4 plus 1/4 times log 4 plus log 2 plus 1/2 log 2, then you get 1.5, I think. Am I correct? So now we're working base 2, so this is just 1
Yeah, that's how I
plus 1/4 log 4 plus 1/4 log 4, right? So what is this? This is 1/2
Why log 4?
plus, because it's 1/4 log 1/1/4. Right?
1/2, 1/2. All
Yes.
of them are 1.
So this is 2. So this is 1/2 plus 1/2, which is that's exactly what it is. It's the number of bits Now, when you don't have exact powers of 2, then you can't talk about bits, but you round up. So up to the rounding error, yeah. There is a theorem about it. I'm not going into it. You want to read Cover and Thomas. You want to know about entropy, so you read Cover, Thomas. I wrote the names correctly. This is the book. At least the first 2 chapters.
The elementary of information theory, this one or?
The one I sent you. Or the one Yael gave you, which I gave to Yael. Yeah, first 2 chapters, then there's more sophisticated stuff, but first 2 chapters. Yes. Okay, but for us, entropy is going to be something very specific. I mean, it's a deep thing. I mean, I have people research this. It's not like okay. So we have this exercise. This gives you information. By the way, consequence of this thing. What is the entropy? So suppose that x is a function of. Okay, suppose we have some function. So okay, suppose x is some random variable, right? So x takes values in g. Okay, and suppose we have some function from G to a different space. The only reason I wrote G here is because we usually have X taking values in G, right? Whatever G is, but now it's just some set. And suppose we have some function from G into, I don't know, some other set H. Doesn't matter, it's completely abstract. Again, entropy doesn't care about where you have values, it cares about the distribution. So it's really a property of distribution, okay? So if we have this, we can ask about the entropy, for example, of fx, right? This is another random variable, right? Or we can ask about the entropy, the joint entropy of x and fx. What should this be? How much information is there if I measure x and I measure fx? Right? The same as what?
It's X over F.
As x. But it should be greater or equal than f of x.
Why is it
Same as measuring just x.
Because X already
Well,
covers the
So
information.
this is a theorem now. I'm saying this. I'm claiming this. This is a claim. Okay. This is not a claim because this we already proved. The fact that the joint distribution has more entropy than the right. Yes. Because this minus this is the conditional entropy, and the conditional entropy is non-negative. Okay. So this is always true, right? But you see that this means that if you take something, if you have a deterministic transformation of something, right? So the entropy of x squared is always less than or equal to the entropy of x. Okay, for example, if x is a number. Okay, so if you have a deterministic transformation, if all the information about f of x is in x, then you don't have more information. So how can we prove this? Well, it's very easy, right? So we need to prove this equality. Okay, how do we prove this equality? Well, it's just a consequence of what we wrote there, right? We just write this. We can condition, right? What is this guy?
0.
This is 0. Why? Because f of x is always measurable with respect to x. With respect to the sigma algebra generated by x, right? Because it's a deterministic function of x. Okay? There's no information. That's exactly what I said before. Temperature is a function of the momentum, right? Or the kinetic energy, say, okay? So if x is the kinetic energy, and if x is the momentum, say, for every one of the particles, right? You can get the kinetic energy out of that, just half mv squared or whatever, right? And so if you average the kinetic energy, you get the temperature, okay? So temperature is a function of the kinetic energy. So it means if you know the momentum of all the particles, then you know the temperature. So the entropy is 0, conditional entropy. But the other way around is not 0. It's not 0. In fact, knowing both temperature and the momentum is the same as knowing the momentum, because the term, and I mean completely obvious if you philosophize about it, but that's the math. Okay?
איך חוץ קדם בפיזיקה?
מה?
איך חוץ קדם בפיזיקה? הקורס שלנו.
מתי שינו מתמטיקה ופיזיקה זה נהיה תיאוריית היפות בפיזיקה לפחות. I mean, you can think about it, like Einstein would postulate like an equivalence principle or something like that, and then you just get all of the math coming out. Like, just one like that. Or you postulate some symmetries in particle physics, and then you start getting, I don't know, SO3. I never understood this stuff. No, but it's really deep, this thing. Yeah. The way physicists know how to use math to do actual things is very impressive. I think deeply that's what physics is about. It's not about actually saying what the experimental physics is about saying which equations, what are the constants in the real world, measuring them and like saying doing experiments. But theoretical physics is about saying what possible physics are there, right? Maybe you can have like many possible physics. So Einstein gave you a field equation, then you have to go measure the constants, right? Right? These equations have to be this. Why? Because gravity and acceleration are equivalent. So everything falls out of there. Something like that.
But not just constants. I mean, it's also a phenomenon that you don't need the constants to know if.
Oh, this is why some theory should be better than another theory, because you go and observe. You can invent physics, right? So you can say maybe I have 12-dimensional, and I just don't see the other dimensions, right? And it would be nice if it could give some prediction, like if it would work exactly as good as everything, but also better in certain cases, then we would use that. Some people say that we should, but so for example, string theory is a very good example where you have like 500 possible different theories, or I don't know how many there are up to nowadays, right? And they can't distinguish between any of them. I mean, so now the experimentalists have to distinguish between them. And the thing is that, but the theory itself is really about what possible physics are there, right? I mean, how do you just do quantize gravity? But they have like an idea why the gravity, if it has a particle, it has to have, spin 2 or something like that, or I don't remember, or what property. I don't know why, but they have these things, right? And it comes out of like some assumptions about like what nature should be like, and then once you make those assumptions, you get like for Einstein, you just the equivalence principle, maybe speed of light is the equivalence principle basically tells you that the speed of light is constant because you can measure the speed of light by doing some experiment. Then you have to get the same answer if you're in a rocket or if your laboratory is moving or not. I mean, the Earth is moving, right? So you have to, if you're accelerating, you have to get the same, right? So then you start getting why the speed of light has to be affected by acceleration, which is completely crazy. And but once you postulate the equivalence principle, then you can like make these sort of experiments and it gives you the equations that you have to have. And or it leads you to a proposal for equations, and these equations satisfy everything, and nobody had a better or simpler idea. And for other cases, it's a bit worse. So it's not the same. Not the same. In string theory, we don't have enough restrictions. We need another postulate. Right? We need another okay, it should obey some symmetry. Then it will throw out all the 499 other candidates and leave us with one or something like that, or maybe with a few that we can measure. But I don't know enough about string theory to say, and that's too much already. Okay, so now what did I want to say? Okay, good. So this was one thing. Let me give you some more exercises, which will actually hopefully appear on a sheet at some point, an exercise sheet. You already have an exercise sheet currently, right? But the next one will be on entropy. So let's see. This is a bit involved, but you just need, I'll give you a few steps maybe on the exercise sheet. So exercise, we don't need the full force of this thing, but let's write it anyway. I mean, it's nice. And it's basically using just martingale convergence. We already proved, remember, things about martingale.
The continuity of
So assume that Fn increased to F infinity, which is the sigma algebra generated by the union of Fn. These are sigma algebras. In case everybody understands what I'm writing here. Increasing sigma algebras, the limit is the sigma algebra generated by the union. And sigma n are going to be decreasing sigma algebras. They decrease to sigma infinity. And here we don't need sigma algebra generated, but this is just the intersection of all of them, because the intersection of sigma algebras is a sigma algebra. Okay, so we have increasing or decreasing, and then the entropy. So assume that we have some finite entropy here. Some guy with finite entropy, okay, this is important for, then conditional entropy of Fn, this will, well, first of all, the bigger they get, which direction is this going? This is monotone, this is, right? It's from the other axis, right? The bigger this gets, the harder they fall.
Yeah.
Okay, so this goes down, right? Because you get more information, conditioning on more information, and it goes down to what? To the maximal amount of information. I mean, this is completely intuitive and it's true. True because of the monotonies. Okay, and what about the other one? The other one will increase, right? And then this will increase.
These are numbers, right?
What? These are just numbers. So this is one exercise. You should think of how to prove this. It has a few stages. I will give it on the exercise sheet, maybe broken into a few stages. Let me also say another thing that we might want to use in the future. Actually, no. So let's move on to the entropy criterion. Okay, so I need my first lemma is going to do, now I'm going to do random walks. Okay? So, random walks and entropy. So proposition or lemma, let U be symmetric, adapted, exponential moment. I don't need exponential moment, this, but I'm just writing that because that's what everything we work with here. And I need to guarantee that I have finite entropy. You should check. You should actually check. It's not very difficult to check. That as long as mu has a logarithmic moment, okay, which is much weaker than a first moment, okay, then the entropy is always finite. Okay, but all we need here is finite entropy to be discussing what we're going to write down. Okay, so let me write. I'll write in a different color. So assume, and this is when I wrote SAG infinity, then
Exponential moment.
I actually it's exponential moment, and I don't care. I don't need this assumption in blue, but I'm writing it down because it's the actual assumption that I need. Okay, so you assume that mu is a probability, right? So you can assume that mu has finite entropy. This h of mu is the same as h of x1, right? If x is there. Okay, so I'll let xn be a mu random walk. Okay, so it's just a process to get by multiplying independent mu elements. We use the notation ft. This is the natural filtration, so it's x0 up to xt. And we're going to use sigma t. This is going to be the tail filtration. So it's xt plus 1. It's not a filtration. The sigmas go down. Sigmas are decreasing, the FTs are increasing, just like. Okay. We haven't talked about tails. Maybe we will in the future. That's more relevant to.
We are assuming the exercise, right?
What?
We're assuming we know the exercise.
Yes, this is the music. Okay.
Yeah.
Well, at the moment, I'm not exactly assuming it, but for this same proposition, I didn't say what it is. I just wrote down the notation that I'm going to be using. And what I want to say then, I can measure entropy of the following. So for every k, I want k is equal k less than n and some n integers. Okay, then I can look at x1 up to xk conditioned on xn. Now let's think intuitively for a second. I'm looking at some random walk. I'm asking for the entropy of the first k steps of the random walk. Okay? And I'm conditioning on what? On the future. Now, if I know where I am at time n, the rest of the random walk is going to be independent of what's going on here. So what's going to happen is that this is going to be equal to everything. You can condition everything into the future. This is conditioning on everything into the future, right?
So once you condition on one thing.
Once you
in the
condition
future,
on the one thing in the future, you can condition on everything in the future. Okay?
but what's
And of course, you can condition on anything in between. So this is also equal to, so let me write this. This is equal to xn plus m,
This is how you prove.
okay? And this is equal to x1 sigma n. Okay? That's the first statement. And from this, we can get a consequence. Okay,
What does it mean to take entropy of x1, x2?
well, you can just think of them as something taking values in a product. I mean, in a couples, k couples, right? So it's still a discrete thing, and you can do the entropy of that. Again, we don't care about the actual values; we only care about distribution. So it's a probability distribution taking values in some abstract space. Okay. Joint distribution of these things. Okay. These are not independent, right? There's the steps of the walk. They're not independent. Okay. Okay. So I want to prove this. Okay. So proof. How do we prove it? Well, let's let's first look at the joint again. How do we do conditional entropy? We do joint minus something, right? We have a formula. So we do x1, xk, xn, right? And we need to figure out what this is. We need to somehow get it to be looking like this, right? Once we do this inequality, we send m to infinity, we get this, right? Because that's exactly increasing sigma algebras that will increase to sigma n.
But show this one with
Okay, so
Markov properties.
So this one, let's say this is easy. This is from the exercise. Right? Because these, as n goes to infinity, they increase to sigma n. So that's just the exercise. Okay? So what we need to prove is this. Okay? Okay, so what is this guy? Well, let's start maybe with the other side. Okay? So xn, so I'll start with this one, up to xn plus m. Okay? So what is this? Now, intuitively, what can happen is that we can peel these off. Why? Because once we condition on this, we kind of know how to start independently. So let's define, so n is fixed now, right? So we can define yt. Let's define yt. What is this? It's going to the random walk started from xn. Okay? So at time 0, it's at xn. Okay? And at time
So x equals n.
yeah, so sorry, it's at time 0, it's at xn minus 1 xn plus t. Right? So at time 0, it's at the origin. Okay? And it moves just like the random walk did here. So you plug in an xn. So if you multiply xn on the left, you get back the xn plus t. Okay? So we know by the Markov property yt. Okay, what is yt? Is a mu random walk, right? Independent of what? Of all the information up to xn. Right? Because it's independent. What is this? This is just a product of all the u's, all the steps between time n and time n plus t, right? And those are always independent of everything that happened up to time n. So this is independent of
What about
Fn.
x to the minus 1?
F independent of Fn. What?
What about x1 to the minus 1?
No, I defined it to be this.
Okay.
Okay, so this would be equal to, what it would be for un plus 1, un plus t, where there's nothing in the product.
Oh, that's how you cancel out the first.
Yeah.
Okay.
If it's not too much like write explicitly how we use the Markov property, or should we just
This is what the Markov property says, right? The probability that this is equal to something or any marginals are equal to something, conditioned on the first n steps, right? These first n steps are determined by the u1 up to un and x0, right? And so this is determined by these. So but these, everything that goes into defining yt is independent of these. So they're completely independent. And it behaves like a mu random walk because you just multiply by a mu independent element. Okay? In fact, the way I defined it, I don't need the Markov property. There's no Markov. This is just product of elements. Just one.
Yeah.
Okay, sorry, it's not the Markov property. Because I resent it. I removed everything to be starting from 1.
So it's not independent. It's independent of Fn because you don't need Fn.
Yes, it's independent of Fn because Fn is generated by
u1 to u.
x0, u1 up to un.
You don't need.
And it's independent of these. Okay. So I don't even need a lot. Okay, now the thing is that this entropy that I'm trying to calculate, write it again. This entropy that I'm calculating, well, I can rewrite it as a different entropy, right? x1 up to xk. Then I'm going to write xn. Okay? And then I want to know xn plus 1, but instead of knowing xn plus 1, it's enough to know what y1 did. Okay? So when I write y1, y0 is always 1 by definition. Right? y1 up to yn. Now, why are these two entropies equal? Let's see. This whole n plus k tuple, okay, is or n plus 1 plus k tuple is what? Is a function of this, right? If you know all of these numbers, not numbers, if you know all of these values, then you know all of these values because each of these can be computed as a function of these.
and also vice
Right?
versa?
But also the other way around. If you know all of these guys, then to get back to here, all you need to do is take all of these and multiply them by this one that you know. So this tuple is a function of this tuple, and this tuple is a deterministic function of this tuple, right? And so the entropies are equal, because they're each less than or equal to one another, right? This is just rewriting the information in a different way. But why is this good? It's because these are independent of these. Right? This tuple is independent of this tuple. So this becomes the entropy of x1 up to xk, xn, plus the entropy of y1 up to yn. But what is the entropy of y1 up to yn?
Like the random walk of
It's the entropy, just x1 up to x. Right? Because it's just a new random walk.
Wait, okay, sorry. Why is y1 equal to xn plus 1?
nothing, but it's a function.
No, it's a function.
Like they have the same entropy.
If I have this, I can get all of these
Right.
by taking all of the last ones and multiplying them, using this one, multiplying it on the left, inverse on the left, and get this. Then there's a function to go from this tuple to this tuple by taking this one and multiplying with the positive sign on the left. All of
Okay,
these.
so you have the x1 to xk, xn, and then you have a function fx and gx, right? And
Yeah, so this is a tuple,
right.
and it's some function of the above tuple. And this is a different function, which is a function of this one. So each one of them is less than or equal to the other one, so they're equal.
So we use the extra step.
Okay, if there are two functions, one gives you to go from one place to the other, right? So, example, if you have two linear equations, okay? Right, if you have they have a unique solution, then you can go in between, and the entropies would be the same. Here it's a bit more complicated. Well, it's a distribution. I mean, if you have some way of going back and forth, it's a bijection.
Yeah.
Okay? The function taking this tuple to this tuple is a bijection. This means that so what do we have? So we have this. So we got the original thing plus this thing x1 up to xn, right? But you see, this cancels out when I take the difference, right? I could have taken also m equals 0, right? M equals 0 would be this there would be nothing here, okay? And I would only have this one. So so when I subtract, what did I want to say? No. So yeah. So now now I want to subtract xn up to xn plus m, and here I want to subtract xn, right? So I need to say something about entropy of xn up to xn plus n. And this is equal to entropy of xn y1 ym, same reasoning as before, and go in between them, right? But this again is independent of xn, so I get that this is equal to the entropy of xn plus, and the y's become x's because this is just the same distribution. Now you see that I have this thing. I have this is the same, right? So when I subtract all of this entropy and subtract all of this entropy, right? So let's call the ones I'm subtracting. Subtracting this and this, right? That's the conditional entropy that I have on the left-hand side here, right? So the two circles, the difference between them gives me that one. That circle. Can you see the circle? I don't have this. The two circles give you this. Right? The blue circles give me this blue circle. Okay. And the blue square, right? And so the underlined cancels, and what you're left with on the other side is the difference between the two squares. Difference between these two squares exactly gives you this. So that's a proof. Well, I'm only convincing you. You can do it on your own. That's what I'm actually.
We are convinced.
The whole course is just giving you enough self-confidence to do it on your own. Okay. Consequence, corollary. I want to calculate, for example, h of x1 up to xk and xn. Again, k is left. Okay, suppose I want to calculate this. What do I get? Well, condition and add, right? When you have tuples, you can condition and add entropy, right? So I condition. Okay. Sorry, that's not what I want to do. Well, it's true what I wrote, but it's not what I wanted. So I want to do the other thing. I want to condition on x1. I want to condition on x1. So I'm going to write this again as the entropy of, now you have to be careful. So we're going to, so let's define. It's not exactly corollary. Okay, let me write it. I'm going to do it a bit quicker now. So this entropy is equal to what? It's equal to I can do x1, right? And then I can look at x1 to the minus 1, x2, up to x1 to the minus 1, xk, and x1 to the minus 1, xn. These are my y's now, right? I'm allowed to do this because it's a bijection, right? The tuples are in bijection with each other. Okay? Now, this whole thing is independent of this guy. Same reason as before. No x1, this is just a random walk, independent.
But you wrote like this because you're using the same idea as white, right?
Yes. So this is equal to the sum of two entropies. This and this are independent, right? So this is x1 minus 1, x2, up to x1 minus 1, xk, x1 minus 1, xn. But what is this? This is a what? This is a random walk. It's taking k minus 1 steps
Starting
and then n minus 1, right? So this is the same thing as hx1 plus h of the same random walk, so I can use x's again. But now it only goes up to k minus 1 and n minus 1, right? Now keep going until you finish the case. Do again x1, right? I mean, now just use induction or something.
What is that again?
again with the functions.
So how many guys do I have here? I have k minus 1 guys, which exactly represent a random walk, and something at time n minus 1, right? It's not at time n, it's time n minus 1 actually. Okay?
But you don't begin from the origin.
I do begin from the origin. I do begin from the origin. This is one step. If you want x1, this also includes x1 to the minus 1, x1, which is the origin. That's the new 0. So this is y1, this is y k minus 1, this is y n minus 1.
Right.
So y0 is 1. Okay?
Can you say we are using the group structure here?
Yes. So you get a bijection. I can shift things. If I multiply on the left, just shift around the walk to a different starting point. If I shifted it to the starting point, the origin, just get a new random walk with the same distribution.
Left multiplication is like isometry of the.
Don't need isometries. I just want it's a bijection. It's a bijection. I can go back and forth. So now I get the same entropy.
Because no, it's like for Shire graph it wouldn't work.
It's also not true. All these equalities are not true for short graphs. Otherwise, we would have very weird consequences. It's just not true. Okay? In general, I mean, it could be true in some cases, but you have to be careful. So there is some deep symmetry here about groups. Really, it might be, well, okay. There's deep symmetry here about groups. The fact that it's product of independent elements, it's not even about transitive graphs, it's like really about groups, the way I'm doing it. Okay, so the entropy of x1 plus this. So if I continue this way enough times, or again, I get k times one step, which is, by the way, h of mu. H of x1 is h of mu, right? Same thing. Plus, what do I need here? How long does it take me to go from k to n, right? So n minus k steps, right? Which is what? Which is the entropy of the convolution of mu with itself n minus k times. Did we talk about convolutions? I don't remember if we talked.
Know it from other courses.
But, okay, so I didn't even define it. At some point I will need to define it. Good, so that's what I would think about entropy, and we should remember it. definition, okay, break. And then we do random walk entropy. Okay, finally.
של קיימנוביץ', כאילו כל הבנייה הזאת לשם. עכשיו, כשרק התחלתי לקרוא